Hello, everyone, and welcome to the Microsoft Academic Research Exchange. I'm Marcy Collinson, Director of Worldwide Academic Research at Microsoft. In this session, Andy Howard, Senior Program Manager for Microsoft's Azure CycleCloud, provides an introduction to how to get started with CycleCloud Workspace for Slurm and integration with tools like Open OnDemand. If you have questions, you're welcome to submit them anytime during the presentation using the live meeting chat. Welcome, Andy, and thanks for being here today.
Thanks, Marcy. Welcome, everyone, to our introduction to CycleCloud and CycleCloud Workspace for Slurm. My name's Andy Howard. I'm a Senior Program Manager on the Azure HPC and AI ecosystem team. I'm the lead PM for Azure CycleCloud, which is our main topic for today. I've spent 20 years in the HPC space. I've worked for research institutions. I've worked for the DoD. I've been a consultant for private companies, and I spent the last 8 years doing HPC at Microsoft. So kind of the agenda of what we're going to go through today, just a general overview of what is CycleCloud, why would you use it? For those of you who aren't necessarily as familiar with the HPC space, what is Slurm? And then introduction into our newest tools that we have specific to CycleCloud and Slurm. And then we'll go through a quick demo of the capabilities of CycleCloud in general. So when we talk about HPC and AI workloads on Azure, there's kind of this whole spectrum of customers that we have to focus on, because what we're really trying to address is meeting the customers where they are in their cloud migration journey. You have some researchers who just want to submit jobs, get their work done. They don't care about necessarily the underlying infrastructure. They don't care so much about controlling all of the topology, when things are spun up and down. They just want to submit a whole bunch of jobs and get the results. So that's kind of the lowest effort to science as we think of it. On the complete other end of the spectrum, you have customers that want to build out and deploy their entire end-to-end infrastructure. So they want to create things like VM scale sets and VMs and virtual networks and disks and all of those pieces that you need to build an HPC cluster. They also want to control all of the software configuration, whether it's the scheduler, the deployment, the user management, the application installation. They want to do it all themselves. And both of those things are completely fine. But we find that a whole lot of customers that come from the on-premises HPC world really want an easy onboarding tool to run the workloads as they exist today and as their users are comfortable with, in an easy manner on top of Azure's infrastructure. So they can take advantage of the capabilities and flexibility of Azure without having to worry about the complexity of modifying that architecture to fit in the cloud. And so that's really where CycleCloud comes in. It sits in the middle of both worlds of, I just want to submit jobs and I want to control everything. So CycleCloud is really designed to allow HPC admins really to provide an easy way to orchestrate, manage, and provide access to their users to Azure's HPC and AI infrastructure. So it allows you to deploy the infrastructure. It allows you to create and destroy compute resources on demand. And it allows you to create and mount the different types of file systems that are typically used within the HPC world. So what is CycleCloud exactly? Well, it's basically a downloadable, installable software product that's designed mostly for enterprise, but also, academia and research workloads, really just HPC workloads in general. And it allows you to deploy the scheduler, deploy the compute nodes, manage the storage and networking that's associated with those things. And it also enables a lot of burst workloads, which we can get into a little bit later. But another big question that I get from, especially my field all the time and customers is, well, what doesn't CycleCloud do? And the biggest misconception that we see is CycleCloud is not a scheduler in and of itself. If you need a native Azure HPC scheduler, that would be Azure Batch. CycleCloud is really just focused on connecting the scheduler to Azure infrastructure. So it's really kind of that intermediary piece. You can think of it more of like an infrastructure orchestrator rather than the scheduler piece, but it does the orchestration in a job-aware way. We integrate with all of the common job schedulers. Slurm is by far one of our most common ones. IBM LSF, PBS Pro, and Grid Engine are some other ones that a lot of our customers use. We also have the capability to integrate your own custom job schedulers. A lot of times when we start to work with really large enterprises that have been around for a long time, some of them may have their own custom needs. And there's also new HPC schedulers that are being developed all the time. So we have a common API layer that all of those can integrate with, which we call scale lib, and we'll talk about that in a little bit. So why would you choose CycleCloud over something like Azure Batch or even something like Azure Kubernetes Service or any of the other offerings on top of Azure? The biggest reason is if you have a need or your customer has a need for existing HPC schedulers, we integrate with most of those already. So it alleviates that need to actually do the integration work themselves. It also provides the ability to clone or lift and shift, if you will, an existing HPC cluster from on-premises into Azure. Another big selling point that a lot of customers are interested in, and we'll look at this a little bit more in the demo, is you don't manage just one cluster with CycleCloud. You can manage multiple clusters. You can manage multiple clusters in multiple regions. You can manage clusters that allow access for different user groups in different areas of your institution, and basically isolate the ones that they need to have access to from the ones that they shouldn't have access to. And then the other big piece, and this kind of goes back to the first topic or the first point about the scheduler integration, is we do all of this orchestration in a job and topology aware way. Meaning, if you don't have any work to do, if there's no jobs in the queue, we're not going to spin up infrastructure. We're not going to start VMs and leave them running. And once the work's done, we'll spin everything back down. When we do spin things up, we want to make sure that it's in a way that can actually run the jobs. For single node jobs, for single core jobs, this doesn't matter as much. But when you start talking about jobs that scale to, 5, 10, 20, 40, 100, 1,000 VMs, all of a sudden that topology awareness really matters. And so we take that into account with our autoscale library. So this kind of just highlights the overall idea of what the typical deployment model or how customers kind of migrate from on-prem to the cloud. So they take their existing on-prem cluster today through CycleCloud, and whether it's the data scientist interacting with CycleCloud and doing this creation, whether it's the line of business manager who just wants insight into what's going on, or maybe the IT admin who just wants a tool to make their job a little bit easier, they interact with CycleCloud to clone that cluster into Azure. So if we dig a little bit more into like the CycleCloud architecture itself, we have the CycleCloud piece is, like I said, an installable web app essentially. It has both a web app UI component and it also has a command line. It also has a full REST API. So some customers have actually fully automated their interaction with CycleCloud with existing tools that they have on-prem today. So CycleCloud itself consists of the REST API, like I just mentioned, an orchestrator, which is the piece that talks to Azure to deploy and manage the VMs themselves. There's a monitor component that keeps tabs on what VMs are still running. So after the initial request comes in, make sure that everything's still running, still healthy. If anything has happened, reflects that back to the IT administrator or the uh, cluster administrator. We also have this notion of CycleCloud projects, and this is how we get the software installed and configured on the nodes themselves. So it's easy to create a custom image that has all of your applications, but most of the time you need to do some sort of last mile configuration to wire the pieces together, right? You need to have compute nodes that join back to the scheduler. Maybe the scheduler needs to know things about the different file systems, the users that are supposed to be associated, that sort of thing. And then also the monitoring components. So all of that's done via CycleCloud projects. Those projects are deployed via Azure Blob. So you create a storage account with a container inside of it. All of those projects get uploaded. And then as your VMs spin up, they're able to pull that information down, do their configuration, and then actually tell CycleCloud and the scheduler, hey, I'm ready to go. I can run jobs now. And then if we look at the cluster side of things, it's a fairly typical HPC deployment, right? You have a head node or a scheduler that users either log in directly to the head node, maybe they log into a login node that has access to that head node. They submit jobs. And then we have this component that, when you look at this slide, there's demand calculator and auto scale lib. Those two pieces are basically our scale lib offering. And that's kind of the magic inside of CycleCloud. So first is the demand calculator. For some schedulers like Slurm, it actually does that demand calculation on its own. It will basically go and look at the queue, see what jobs it needs, what resources they need to match to, and then tell CycleCloud, hey, I need these resources. But other schedulers, PBS, LSF, Grid Engine, don't necessarily have that demand calculation built in a way that they can reach out to external APIs. And so that's where we have this demand calculator where we actually go and look at the queue, process the jobs, and then try and do a best fit match of what resources do we need to allocate uh, in response to the jobs that are there. So then we have the autoscale library itself. That's the piece that's responsible for talking back to CycleCloud, makes the REST API calls to say, I need these VMs, or I need X number of VMs, or I need X number of cores, or this many GPUs. There's a bunch of different ways the request can be made, but the autoscale library is what enables that in a way that we can scale it to different schedulers without having to rewrite everything from scratch every time. Then when it comes to the execute nodes, this is another challenging part of writing all of this yourself is these nodes are dynamic. So most of these tools, most of the legacy HPC tools and schedulers were written in a way that assume a fixed infrastructure. So you spin the cluster up one time, you turn everything on, do your burn-in tests, wire everything, configure it up, and then you leave it. Unless there's something that goes wrong, it's running 24/7, 365. That's not the case when you're running in a cloud environment. And so the execute nodes actually need a lot more information to be able to spin up and down in a dynamic way. They need to know, do I have any work to do? Should I even be turned on right now? If they're not on, they get that power on signal from CycleCloud. And then when they spin up, they don't really know anything about where's my scheduler? What file system should I mount? What users should I add to this? And then finally, once they start running jobs, which jobs do I run? So that's where CycleCloud has an agent that runs on it. We'll talk about that in a second. That does that constant feedback loop between the compute nodes, the scheduler, and CycleCloud itself. We also do that last mile configuration to provide all of that information so that the nodes can actually join the scheduler. And then finally, you have the application stack. So when I mentioned projects earlier, there's kind of a couple different ways that you can do the user space application side of things. Some customers choose to install those on something like an NFS file server, and that way it's mounted across all the nodes. There's no extra installation steps needed. Others may need to do some last mile configuration and choose to install it on the fly. And then other customers choose to install it into a custom image. That way it's just there and ready to go as soon as the node comes up. So all of those are valid methods for getting the application stack installed on your nodes. So if we dig a little bit deeper into that architecture and the different components that are involved, there's Cycle Server. So this is where I say CycleCloud itself is not an Azure service. It's not something that you just go into the portal and it's running on the back end. You don't have to worry about it. It is a web app that you have to deploy and manage. The good news is it's easy to deploy via marketplace image. It is just one VM. It doesn't cost a lot to run. You can even install it on-prem if you want. We have some customers who choose to do that. It doesn't really matter where it runs. At the end of the day, it's a web server with a UI, a data store, and CLI components. That's really it. There's the CycleCloud CLI, which can be installed. It's installed by default if you deploy from the marketplace image on the CycleCloud VM itself. You can also go and download that locally and run it on your local machine. You can run it on another VM. You can run it on the scheduler node. It can run basically anywhere. It's just a CLI way to interact with the product. Jetpack is that bootstrap component that I was talking about earlier. This is an agent that gets installed on all of the compute nodes, the scheduler node, anything CycleCloud touches gets Jetpack installed. It's essentially that interaction point with CycleCloud. ScaleLib is the autoscale library that's installed on just the scheduler node. The nice thing about this too, this actually enables our hybrid and burst scenarios. So you can download ScaleLib to your local cluster's head node and create that link to CycleCloud so you can actually burst from on-prem to the cloud. That's a little bit of a more advanced scenario that we might get into in future webinars. There's also cluster types and templates. So we ship out of the box with cluster types that include all of the popular schedulers, like I mentioned before, Slurm, PBS, Grid Engine, etc. But you can also create your own custom cluster type. Many of our customers, especially as they go into production, end up with a custom template that includes all of the various definitions that they want, whether it's additional mount points, custom network configuration, multiple queues or partitions being defined so that they can use different VM types than what we have out of the box. And so it is possible, basically, especially when we go through the demo, everything you see can be customized. It's just a matter of how much you want to put into that cluster itself. And then one of the newer components that we have is the node health agent. One of the things that we've realized, especially over the recent years, as this trend of HPC computers being, and with especially with the introduction of AI, these VMs are becoming larger and larger and more complex. We've gone from just over a decade ago, 2 core VMs being the norm. I guess that was more closer to 20 years ago, but two core VMs being the norm to now we have 192 core VMs. We've gone from single GPUs being bleeding edge to now we pack 8 GPUs in a box. A single InfiniBand interface was crazy back in the day. Now we have 8 in every VM, right? And so as we add more and more components to these machines, and as we scale them out more and more, so we're not talking about a, you know, 2-node cluster, we're talking about hundreds or even thousands of nodes. The potential of things going wrong grows exponentially. And so we've introduced this node health agent that not only checks when the node comes up, is it healthy, but also throughout the life cycle of the node, runs these periodic checks in a job-aware way. Because the other lesson that we've learned over years is we can't just run health checks across the cluster whenever we want to. A lot of these health checks, especially if you're checking the performance of components, will start to impact jobs. And so we have kind of 2 classes of health checks, what we call intrusive and non-intrusive. Intrusive health checks we only run when the node is idle, so at boot or in between jobs. But then we have this other class of health checks that things like checking to make sure the InfiniBand links are still there, checking to make sure the GPUs are still there, checking to make sure that we're not throwing a bunch of memory errors. Those are things that we can do in a relatively non-impactful way, and we can do that while jobs are running. So if you've got a 9-hour job and halfway through we detect, hey, by the way, you've got a few nodes that the IB links are starting to go up and down, we can actually throw those errors and allow sysadmins to take action on that. Maybe they want to let the job continue to run because in some cases it doesn't matter that much in terms of performance. In other cases, they may want to actually stop the job, do a checkpoint, take that node out of service and have a new one provisioned. Um, the nice thing is for the actions that we can take automated action on and wouldn't impact jobs, CycleCloud will handle that replacement automatically, again, in a job-aware and topology-aware way. So I want to shift focus just a little bit now into one of the main schedulers that we integrate with. For the last probably 5, 6, 7 years, Slurm has been growing in usage. We see a lot of customers asking for Slurm. Depending on the month that you look at our usage reports, Slurm tends to dominate most of our schedulers that customers are using. So it is one of the top HPC job schedulers on the market. The part of the reason for that is it's free and open source, so anybody can access it, download it, deploy it. It sees a huge amount of success in academia and research environments. The nice thing about it is it does have an enterprise support option. So SCEDMD provides full enterprise support packages that customers can purchase, even if they've been using it for free for years before that. It scales to hundreds to thousands of cores, even hundreds of thousands of cores. It's got really robust job accounting for large multi-user, multi-workload environments. This is really important for doing things like chargeback, especially when you start to move to the cloud. All of a sudden, there's this cost aspect that wasn't always that important to track on-prem. Now it's pretty important to figure out, okay, who just deployed, a bunch of expensive GPU machines and had jobs running on them for months on end. But it does have really tight integration with Azure CycleCloud. So we work really closely with SchedMD as well as the other scheduler vendors to make sure that the Slurm experience on Azure is best through CycleCloud. Point blank, that's the easiest way to get up and running. We handle all of the Azure complexity while Slurm handles all of the job and scheduling complexity. And then finally, one of the big things, especially with the rollout of some of our latest GPU SKUs, topology awareness for both InfiniBand and NVLink deployments. With the advent of GB200s and future generations of NVIDIA GPUs, that additional topology awareness for NVLink is really, really becoming critical. And not just in terms of the job scheduling, but also in terms of how we actually deploy and allocate the VMs on the Azure side. So that tight integration is really critical for most of our customers. If we dig in a little bit more into the actual integration with CycleCloud itself, we actually take advantage of Slurm's power save mechanism. This was developed back in the day for on-prem customers who wanted to power down nodes when they weren't being used and then power them back up when jobs came in the queue. That same model, it turns out, works really well in the cloud because that's exactly what people are wanting to do. They want to turn nodes off when they're not using them, turn them back on when they have work to do. So the cool thing about Slurm's integration is the scheduler there, Slurm, is actually responsible for telling CycleCloud, I want you to power on these specific nodes. And so this is where we really can take advantage of Slurm's robust topology awareness and ensure that if a job requests a specific breakdown of I want these tasks to be ran on these nodes, these cores, with this memory, this GPU, this CPU, Slurm can decide all of that and just tell CycleCloud, start these nodes. In return, CycleCloud upfront tells Slurm, hey, I have all of these VMs available to you. This is what they look like. Tell me which ones you want. So it's a really nice symbiotic relationship there. We also have, again, robust integration with Node Health Agent. And so we run Node Health Agent not just when the node boots, we also run it anytime a job starts through Slurm's Prolog. We run the non-intrusive tests during the life cycle of the job. And then when Slurm actually finishes a job, we run the health checks again through an epilogue. And so it automatically handles the replacement of those unhealthy nodes and communicates that with Slurm. And then finally, when it comes to the job accounting, it's nice to know the things that Slurm already accounts for. Things like what's the memory utilization, CPU utilization, who was using what when, what's the overall utilization. But then there's other aspects that are kind of cloud specific, right? If you want to do things like cost reporting, for example, you need to know what VM type were they allocated to. What's the cost of that VM? Was it a spot VM or was it on demand? And so all of those things are where we actually start to inject additional data into the database as we allocate those nodes. So it's a really tight integration with CycleCloud and Slurm's built-in job accounting that enables a lot more detailed metrics and reporting to our customers. CycleCloud's great on its own. It's provided a lot of benefit to customers over the years, but one of the things that we noticed is CycleCloud itself really only manages the compute portion. We can tie it to things like virtual networks and storage accounts and different external offerings. We can tie it to things like Open OnDemand. But for the most part, CycleCloud itself just does the compute portion of things. It doesn't manage your storage accounts. It can't create a managed Lustre file system. It can't create subnets and virtual networks. So CCWS was built basically to be an easy onboarding solution because this was a big friction point for us getting customers onto Azure and getting up and started. So why do you want to use it? It's because you don't have to go and manually deploy all that infrastructure yourself. You don't have to learn which components are required to run an HPC cluster with CycleCloud and then go and deploy those. It does it for you. How do we do that? It's an Azure Marketplace solution. You can also deploy it through the Azure CLI. And we'll take a look at that in the demo in a little bit. So we specifically targeted Slurm for our initial CycleCloud Workspace deployment because of the fact that Slurm is, our largest scheduler that we've seen demand for. So again, it's a marketplace application. You can think of it as basically a predefined landing zone. So it's a very prescriptive way of deploying clusters. So it consists of virtual networks and subnets. You can define different storage solutions, whether that's Azure NetApp Files, whether it's AMLFS for Lustre, whether it's just straight up NFS off of the scheduler node. All of these are options for storage on the cluster side. It also deploys the CycleCloud VM for you. So even with the marketplace image, there's some extra steps that you have to do to configure the VM and get it up and running in a production ready sense. CCWS will take care of that for you. And then finally, it will define, but can optionally start a predefined Slurm cluster. So we have a very kind of fixed definition of what a Slurm cluster is. So this is just kind of a build flow slide to show what this process works like. So we have the Azure Marketplace application that you go through, fill in a lot of fields. We'll walk through that step in the demo, but all of that's done up front. So you do it once, it's kind of fire and forget. Once you deploy that, it goes and creates the CycleCloud VM. The CycleCloud VM will then go and pull the needed recipes and everything that it needs to actually build out the cluster from GitHub. And then it finally deploys and configures the Slurm cluster on the back end. So through a series of, I think it's 5 tabs or so, you can go from nothing running in your Azure subscription to a fully running and configured and running jobs Slurm cluster. But it's not just that portion that's really important. We've actually added some additional capabilities because CCWS can do more than just the compute orchestration. So we've done a really tight integration with Open OnDemand. We'll walk through that in the demo as well. Open OnDemand, if you're not familiar with it, is a web-based tool to interact with HPC clusters. It integrates with most of the common scheduler types. It allows you things like terminal access via web browser. It allows you file exploration via the web browser. And then we've also done some VS Code integration with it that allows developers to kind of iterate really quickly and do the development. Instead of just working in a terminal, they can work in their web browser from any machine that has access to that virtual network. We've also expanded a lot of our monitoring capabilities by building in Grafana support. This has become really important as these GPU machines get larger and larger. People want extra insight into what the actual utilization is, what's going on in my cluster, and they want it more real time than some of the other services that we have can provide. And then finally, one of the things that a lot of our customers have been asking for years is virtual desktop environment integration. And so we've partnered with Cendio to integrate their ThinLinc solution as part of our VDI solution. So it's a native Linux VDI experience. So if we dig into this, like I just mentioned, Open OnDemand, it's a very, very popular application, especially in the research community. It allows a lot of different capabilities, especially for researchers who may not be as experienced with the command line. You can even submit and monitor your jobs via a web interface rather than having to go and type out shell scripts or, learn how to SSH into things. And so it just provides a much better end user experience for customers who aren't necessarily as familiar with Linux environments. And then Cendio ThinLinc, the really nice thing about this is it's not just a virtual desktop. It's not just a normal VNC deployment. It's actually GPU accelerated. And so you can take advantage of our NV series line of VMs where, they have actual hardware acceleration. A lot of these HPC models have really high demands when you start to try and render the results and manipulate the models. And so by having a hardware accelerated solution means that customers can basically replace that really expensive workstation that sits under their desk with an as needed GPU workstation that runs in the cloud. One of the things that a lot of customers ask me when they first, start to look at how do I move to Azure is, you know, lift and shift is great. You guys have all of these native cloud solutions. Like, why would I choose one over the other? I've worked with many customers over the years, but I think one of the coolest stories is a company called Vestas. They're an energy company based out of Europe. And they went through this cloud migration journey starting back in 2021, 2022. And basically, they were already running a bunch of Slurm clusters on premises. They were running multiple workloads across shared clusters, a fairly fixed environment. The same set of resources was shared between different user groups. They all accessed it the same way. And so they came to us and said, "We want to move to Azure. We're doing a cluster refresh. We'd like to look at doing a POC and figuring out if we can run this on your hardware instead." We did the initial POC, found out that the performance was great. And so by using CycleCloud, it was really easy to get that up and running. They could run the exact same workload the same way. They just lift and shifted into Azure. So then they started to onboard other workloads. And as they started to do that, one of the things that they realized is that some user groups weren't necessarily as familiar with Slurm as they were used to just dealing with the fact they had a Slurm environment. And so the more we dug into one of the workloads in particular, the Vestas Climate Library, the more we realized we could actually make the user experience a lot better if we work on the actual workload. And so with Azure engineering and the customer engineering team, they actually retooled the workload to not run on Slurm anymore. Doesn't use CycleCloud, but it's actually switched to using Azure Batch, Data Factory, and Blob Storage. And this addressed a bunch of different issues for them. The first was their users weren't super familiar or comfortable with Slurm. They're data scientists, not developing models, not developing code. They just wanted to be able to pick the data that they wanted to work with, decide what scale they wanted to run at, and submit the jobs. So that's where Azure Batch came in. They also had a lot of data sensitivity here because they were building up this library of climate data over the years. But part of the problem was they didn't have really good access controls on who could read and write where. It was essentially a free for all. So sometimes a researcher would submit a job that accidentally overwrote the data in the library. So that's not really a great thing if you're trying to accumulate this data and archive it over time and have this like source of truth data. And so by reworking this to use Azure Blob and Data Factory, they could actually limit what users could do. So they can only pull data from the library and they can only push the results to a different area. And so that helped with a lot of their access controls. And then it also made it so that they could actually rerun the jobs without accidentally writing over good data. And so it just really streamlined their business process and allowed the data researchers to focus on their tasks rather than learning how do I operate a Slurm cluster? How do I manage data effectively? They just had one workload workflow that they worked through. So this was a really cool customer experience. And the really neat thing too, as the CycleCloud PM speaking selfishly, you would think that I wouldn't like this because it's moving off of my product, but they're still running their other workloads on CycleCloud because they have other areas of research where they're doing turbine design and they're doing CFD simulations, where those researchers actually want a Slurm cluster. They're used to interacting directly with the cluster itself, whether it's through SSH, Open OnDemand, other areas like that. And so they prefer that experience over, oh, you just go to this web portal and click a few buttons. So with all that being said, let's take a dive and look and see how this actually works in real life.
Connect to the Azure portal. Create a resource. Search for Slurm in the Azure Marketplace. Select Azure CycleCloud Workspace for Slurm. Hit the Create button. In the Basics tab, enter the subscription and the region in which you want to deploy. Set your logon credentials. Define users' home directories. Create a new or mount an existing one. Add additional file system if needed. Choose between Azure NetApp files or Azure Managed Lustre file system, depending on your storage requirements. Define the networking settings. use an existing virtual network or create a new one. You can optionally deploy an Azure Bastion or peer to an existing VNet. For the Slurm settings, choose which VM size, OS image, and Slurm version to deploy, and if job accounting needs to be enabled. Set how many login nodes should be made available. Configure the HTC, HPC, and GPU partitions. Review and create. Follow the deployment status. Check the resources created. Display the deployment status. When the deployment is ready, use the Bastion to SSH into the CycleCloud virtual machine. Use the key provided during the deployment. Check the log of the installation. Your deployment is now ready to be used. In the Azure portal, retrieve the IP address of the CycleCloud virtual machine. Browse to that address and log in. The Slurm cluster is ready with a scheduler, a login node, and the auto-scaled HTC, HPC, and GPU partitions.
Connect to the CycleCloud web interface and add a new cluster using the Open OnDemand application template. Give a name to your cluster. In the required settings, choose a region, a VM type, and an existing subnet to deploy in. In the Advanced Settings tab, specify which authentication method to use between Basic, LDAP, or Intra. Here we will use LDAP to authenticate users in an Active Directory domain. Finally, set the NFS mount options for the user's home directory. Start your cluster. A new virtual machine will be provisioned by CycleCloud, and Open OnDemand will be installed and configured. After a few minutes, the Open OnDemand machine is ready. We can retrieve its IP address from the property window and browse to that address to log on. Use the HPC admin account and password to authenticate. We are now on the main page of the Open OnDemand portal. The next action will be to connect our Slurm cluster deployed with CycleCloud Slurm Workspace. Set the cluster name and the login node to connect to, and hit the Submit button to connect the Slurm cluster. Restart the web server to reconfigure Open OnDemand, and voila! You can now use Open OnDemand to browse your file, open a remote shell session, list your jobs, or use your preferred integrated applications. Here we will request a new Jupyter Lab session. Use the provided container, set the duration and the partition to run on, and launch your session. If resources are available, the job will immediately start. If not, it will be queued waiting for CycleCloud to provision and configure a virtual machine to run on. When the session is ready, connect to Jupyter. You can now use Jupyter Lab, open and run existing notebooks, or create new ones. When you are done with your session, free up the resources by canceling your job. The virtual machine will be automatically deleted by CycleCloud.
The Cendio ThinLinc application has been installed on this Open OnDemand with CycleCloud environment. To start a Linux remote desktop session, click on the ThinLinc button. Set the maximum duration and partition to run on. Here the HTC partition has been configured to use the Cendio ThinLinc Azure Marketplace image on an NVA 10v5 machine. Launching the request will submit a Slurm job, and if no resources are available, CycleCloud will provision and configure an instance for you. After a few minutes, once the machine is ready, or immediately if a resource is available, the ThinLinc application panel will become ready. The ThinLinc client can be downloaded from there, and you can use the IP address provided to connect, or you can launch ThinLinc Web Access. Here we start the ThinLinc client using our local public SSH key to connect. Once connected, you can start your work. This machine is equipped with an A10 GPU from NVIDIA. The VGL run command will allow you to offload the OpenGL instructions to the GPU. Once done, release your session. If the resource is no longer needed for other jobs, then CycleCloud will delete the virtual machine.
So in the demo, we've kind of walked through, how do I get started using CycleCloud through CycleCloud Workspace for Slurm. We've dug into getting a Slurm cluster up and running from nothing in my subscription to submitting jobs through Open OnDemand, visualizing the results through ThinLinc, and even monitoring those jobs through Grafana while they were running. I hope you all enjoyed the presentation. Thanks for joining today, and hope to talk to you soon.
Thank you, Andy, and thank you for attending this session of the Microsoft Academic Research Exchange. We hope that you found this presentation insightful and that you'll attend the next webinar. Please join the Microsoft Azure for Academic Research LinkedIn community for future event information.